We're going to discuss locus definitions of conic sections. And then how those locus definitions lead to equations. Like, in other words, these things take us to equations of these things. Okay. So we'll get there pretty quick. All right. I'm going to start with like sort of the most famous conic section, like a circle. If you think about a circle is the set of points that are equidistant from a given point. So in other words, if we have this point over here, we call it h comma k, I might say I want all the points that are at a distance r from that point h comma k, that center. It's almost you want to call it the center. All right. Well, what does that mean? It means that I can go up this way in the r units. I can go down r units. I can go this way r units, or that way r units, and then I can go in any direction r units. And if you look at the points that you start to plot that satisfy this condition, that I'm r units from h comma k, they all lie on this dotted circle. Okay? And that definition is it seems pretty straightforward. Okay? Think of it like a dog on a leash tied to a tree. It just runs around in a circle. Okay? All right. So how do we get an equation for that? Well, we could think of distance. We're trying to make sure that distance is constant. So I'm saying that if we have a point on here, x comma y, that the distance from x comma y to h comma k is always r. So I can write that this way. I can say, all right, distance between h comma k and x comma y is the following. It's the square root of x minus h squared plus y minus k squared. We know this is the distance formula you learned about in geometry, quarter geometry a long time ago. And we're just saying, hey, I want that to always be r. And that's it. You're done. You get the equation of a circle right away. It's usually written the following way. Usually you square both sides. And that's that. That's the equation of the first conic, the circle. So this I claim is fairly common. People know about that and may even have thought about the equation of a circle and distance formula being related. I don't know if you thought about that before, but now you have, right? Let's consider the parabola. Okay? The parabola satisfies this locus definition. It's the set of points that are equidistant from a given point that I'm going to call the focus, and a given line that I'm going to call the directrix. Sorry about that. It's D-I-R-E-C-T-R-I-X, the directrix. Now, I've tried to place this on an xy axis. I'm going to be careful about how I do this. I am going to tell you that the distance that the focus is from the origin is some number p, and it's the same distance from the origin to the directrix. Okay? So my claim is that if you try and find all the points that satisfy this condition, you get something that looks like a parabola. And then I'll do one step better. I'll show you how to get the equation and show you that it really is a parabola. An equation like you might be familiar with. All right, so if we're going to start by trying to figure out points that are equidistant from both of these things, the origin is the first natural point to pick. You pick that point there, right? It's p units away from the focus. It's also p units away from the directrix. So when we start to think about where the next point might be, let's talk about something that can't work. Suppose you thought maybe the next point was out here. You said, okay, that could be a point that works. Well, the problem with that is it's p units away from the directrix. You can see that there. But then this distance has to be greater than p. Right? You know that that distance would be greater than p because it's the hypotenuse of that right triangle. And that right triangle is a leg of p, so the hypotenuse has to be longer. So what does that tell us? It means that if I want to move this far along, if I want to move out to this x value, I'd have to come up a little bit in order to make that work. Okay then. So let's get rid of that stuff. Let's just label. We know we're going to have to have a point something like this maybe out here in such a way that that distance and that distance are the same. Okay. Here's a point that should work, I would think. If you were to go out right here along this horizontal line, y equals p, then at some point on here, there's a point, right, that's exactly a distance of 2p units from the y-axis. Now, how do I know that point's on the parabola? So we know this has got to be on the parabola because that distance would also be 2p units. Okay? And then you can start thinking about moving further. Well, if I move further than that, then I can't stay at a height of 2p anymore. I have to go up a little bit because this horizontal distance got bigger than 2p. So maybe I'm moving like this and like this. And what happens is that anywhere I go, that distance has to equal that distance. And what you end up with is something that looks like a parabola. You can do the same reasoning out this direction. You can almost see why it would have to be symmetric about the y-axis. Because if we look on the left, it's sort of all this blue line, this green line just reflected over, and you get the same set of points. So it just kind of shows why you'd expect symmetry in the parabola, even from the locus definition. So next, let's see if we can build the equation for a parabola using this definition. All right, so we're going to draw an xy axis here. We're going to label our focus. And we're going to, again, insist that this distance be some number p. I'm going to go down here. I'm going to draw the directrix. And that's going to be also at a distance p from the origin. Okay? And what we're interested in is all the points that do the following. So let's say I pick a point out here somewhere. I'm going to call this point x comma y. Well, I'm interested in all such points such that this distance here, I'll call that d1, equals that distance there, d2. As long as that's true, we're on the parabola. We're satisfying the locus definition, which is that we have to be equidistant from the focus and the directrix. Okay. So we just got to label some points and do some distance formulas, and everything is going to be fine. Okay. So let's call this point here. This would be, I don't think 0p is a good name for that point. It's not so bad. I think we can name some other points here. We could name this point for sure. This point's already xy, so I'm kind of happy about that. I can get the distance between 0p and xy. I know how to do that. I need a name for this point down here. Well, it's going to be x comma something, right? That's what I need to figure out. Negative p. That's correct. Okay. All right. So now we're ready. We're ready to get our distances and set them equal. So what do we know? We know that d1 has to equal d2. So we're just going to start with that. d1 we can get by doing the following. The square root of x minus 0, or just x, well, I'll write it out, x minus 0 squared plus y minus p squared. Okay, so that takes care of that distance. Okay, this distance, d2, is going to be the square root of x minus x squared. It's just going to be 0, so I get rid of that right away. And then I get y minus negative p quantity squared. Y plus p. Cool. So we end up with the square root of x squared plus y minus p squared has to equal the other distance, which is just y plus p. Okay, let's just, and then proceed with the algebra and see where it takes us. Okay, so what's next? I guess if we want to, we can square both sides, maybe, get rid of that radical. So we get x squared plus y minus p squared equals y squared plus 2py plus p squared. Let's square this out also. So then x squared plus y squared minus 2yp plus p squared equals y squared plus 2py plus p squared. There you go, just algebra. All right, so what do you notice? Well, the y squareds can go away, the p squareds can go away, and you have x squared equals, I'm going to bring this over at the same time, 4py, but that tells us that y equals 1 over 4p times x squared. And sure enough, that's a parabola. Okay? Now you can go through more involved algebra derivations if you want to move that axis of symmetry away from the y-axis. Then you'll end up like subtracting and adding other terms here, but it's all amounts to the same thing. You're setting two distance formulas equal, and then you end up with some kind of equation. Let's take this for a minute and let's think about this. Ready? So here's our equation: y equals 1 over 4px squared. Let's pretend for a minute that p equals 2. So what does that mean in terms of our picture? Our picture looks like this. The focus is at a distance of 2 units above the x-axis, and directrix is down here. So the directrix has the equation y equals -2. The focus has the coordinates 0, 2. And we know that there's a parabola and sort of goes through this. Okay, so we even know more than that. We know the equation is parabola. If we use these two facts together, the equation is y equals, we plug in p equals 2, we get 1/8 x squared. Okay, so the claim is, based on our derivation, that any point we pick that satisfies this equation should be the same distance from the focus, 0, 2, as it is from the directrix, y equals -2. So let's pick a point and see if this really happens, right? Let's pick, let's try x equals 1. So if x equals 1, we get y equals 1/8 of 1 squared. So y equals 1/8. So somewhere on this parabola is the point 1, 1/8. And the claim is that this distance and this distance is the same. Okay? So let's just make sure that happens. Okay? So to get that distance there, I'll call this D2 to be consistent with the language I used earlier, right? So D2 would equal, well, let's think about that. Let's get the coordinates here, right? So this is 1, -2. So now we're ready to find that distance. So it's going to be the square root of x minus x. So that's going to be 1 minus 1 is 0. So you're going to have 0 squared plus, and then you're going to have the distance of, well, it's positive 1/8 to -2. So it's really 2 and 1/8 squared. Okay, so that's distance 2. Let's get distance 1. Well, distance 1 is going to equal, and we know both points already, so it's going to be the square root of, what do we have here? We've got 1 minus 0 quantity squared plus, and what's next? 2 minus 1/8 quantity squared. All right, let's finish it. So this is going to be 1 plus, And then 2 minus an eighth, I guess you could think of that as, what, 16/8 minus 1/8, or 15/8, right? Oh, we got to square that too. Don't forget that. So this becomes 1 plus 225 over 64. So let's finish. This is going to be 64 over 64 plus 225 over 64, square root. It's the square root of 289 over 64, which is 17/8, which, surprise, surprise, is 2 1/8. Now, if we just go back up top for a minute, just remember, we were taking, if you look at distance 2 here, distance 2 is the square root of 2 1/8 squared. So that also is 2 1/8. And sure enough, we verified that, at least in the case when x is equal to 1, this equation with p equals 2 makes sure that the distance between those points are the same. Sort of a fun thing.